Now we're going to derive the equation for the charge as a function of time. How much charge is on this capacitor at any time t in this RC circuit is what it's called. It's got a resistor and a capacitor, so we call it an RC circuit. So to do this, we're going to use the loop rule. So we're going to use the loop rule, and so we are going to start from right here, and we are going to a higher potential, going from negative to positive, so we're going up a hill. So that's going to be positive E, and then the current is presumed to go in this direction, so it's going to be minus IR, and then we're going across this capacitor at some arbitrary time, and we're now starting from over here and ending up down here, so we're actually going back to from high to low potential, so it'll be minus, the delta V will be Q over C, and that has to add up to 0 by the loop rule. And to find this Q over C is just from caps are quite overvalued. You solve for V, you get delta V is Q over C. So let's go ahead and use that, and what we're going to end up with is an equation very, very similar to what we get with resistive forces. In fact, we are going to have to use separation of variables to get this to work. So my general trick is, first of all, we're going to get dq dt on one side, and we're going to keep that side really, really clean. And that just helps guide you to what you have to get rid of and what you have to move to the other side. So first of all, I've got to get dq dt in there. I don't see dq dt in there, do you? Well, it actually is. Where is dq dt, the rate of change of charge on that capacitor? Hey, it's right here. This right here is dq dt. So I'm going to rewrite this like so. It'll be E minus dq dt times R minus Q over C equals 0. So what I want to do is I want to get this dq dt right there. I want to get that to the other side. So I'm going to start doing that. Got to bring R with it. So here we go. We have E minus Q over C. I'm going to bring that dq dt to the other side, but I've got to bring with it that R. Now, again, one of the tricks here is if you just keep the right side as clean as possible, that kind of helps guide the process. So what I'm going to do is divide both sides by R. That'll give me E over R minus Q over RC equals dq dt. Now we've got the right side clean again, and we're in pretty good shape to go to the next step. Now again, with separation of variables, what you want to do is get all the dq and q's on one side and get the dt's to the other side, and that's what we're separating, the q's and the t's, and then we're going to integrate both sides. So what we need to do in order to do that is how am I going to do this? Well, first, I'm going to start with this. I'm going to just put dq on the q's on the right. That'll give me, and then the dt's on the left, I'm going to multiply both sides by dt, and I'm going to divide by everything on the left side there. So I get dq over E over R minus Q over RC. Now I'm actually much closer to where I want to be. I've got all the Q's on the right side. I've got all the T's on the left side. I've separated my variables. But before I can integrate, I want to do some simplification here. Now, this is confusing to integrate this, so some of you guys don't need to do this, but I do. I want to just make this simpler because, again, when we want to integrate this, I want to integrate du over u and just have it be that simple. So what I'm going to do is I'm going to let u equal this whole mess, E over R minus Q over RC. You might notice, by the way, this E over R, that is the initial current. That's going to come in handy later. Let's see. Let's go ahead and what is du? Now, to figure out what du equals, some people find it easier to just find this.
du dq. It's like the derivative of u with respect to q. That for this derivative, that derivative is going to be 0. So that's 0 minus derivative with respect to q of this is just 1 over rc. Okay, and then to get du then, I'm just going to multiply both sides by dq. That gives me negative 1 over rc times dq. So I found what du is, and I've got what u is. I'm going to erase this. The only thing I need to find here is what is dq? Well, just solving for dq, you get dq equals negative 1 over, or negative rc rather, times du. So with these three things, I can rewrite this equation like so. So dt, that stays the same, equals, for dq, I'm going to write negative rc times du. And this is just going to all be over u. Okay, now I'm really close to having du over u. Again, trying to keep the right side clean. What do I got to get rid of? Well, I got to get rid of this rc and this negative sign. So that'll give me negative 1 over rc times dt equals du over u. Now I am ready to integrate. You're going to integrate both sides. And when you do that, you get, this is just a constant, negative 1 over rc times the integral of dt. Well, that's easy. And then on this side, integral of du over u. And so when I do that, I get negative 1 over rc times the integral of dt is just t plus c. Some constant, integration constant, and on this side, it'll be ln of u. Now, you officially, for general purposes, have to have absolute value signs around that u, but because this thing is always going to be positive, I'm just going to leave those off. Now, I'm going to distribute this. Now, this c, this gives me negative 1 over rc times t, plus this is just going to be some other c. It's just going to be, I'll call this c1, and this will just be c. I just distributed that. And this equals ln of u. Now, what do you do next? With this situation, you've got to raise e to both sides. So I'm going to raise e to this whole side, and then I'm going to do e to this whole side. And then what that gives me, and this is always done with separation of variables, this will give me e, again, e to this plus that is just like some constant times e, because it's going to be e to the negative t over rc times e to the c. Remember, when you're adding exponents, it's like multiplying. I'm just going to call this k. Let's not use that. Let's just call that k. That gives me k times e to the negative t over rc equals, what's e to the ln of u? It's just u. So this gives me k times e to the negative t over rc equals, well, what is u? We got to go back up and find out what u is. I happen to remember that it's e over r minus q over rc. Okay, next step is, what the heck is k? Now we got to go to our initial situation here to remember that. What is k? Well, at time equals 0, we're going to close this thing. So this actually gets closed at time equals 0. So at that time, what do we know about what's going on? Well, when you first close it, how much charge is on there? Well, as you can probably guess, at t equals 0, q equals 0. So k times e to negative t over rc, and this becomes 0, which means I just get k equals, when q is 0, this is just e over r. K is just e over r, the initial current. E over r times e to the negative t over rc will equal e over r minus q over rc. Now this isn't canceled. That's only when time is equal to 0 is that canceled. So I'm going to bring that back here. And I'm going to have to move this around just a little bit to get into the form I want it to. I'm going to move Q on this side and move everything else over on that side. So I get Q over RC equals E over R minus E over R e to the negative t over RC. So solving for Q, what do I get? I'm going to multiply both sides by RC. Q equals, and that's a function of time now, it gives me E, I'm multiplying both sides by RC, E times RC over R minus E times RC over R e to the negative t over RC. And this cancels right there and cancels right there. And now I'm getting really, really close. I've got Q equals CE times, I'm going to just factor that out, 1 minus e to the negative t over RC. So what the heck is this? CE, that is the capacitance times the final delta V. That just happens to be Q max. So Q equals, another way to express this is Q max times 1 minus e to the negative t over RC. And if you recall from back in resistive forces, we call this thing that's under there the time constant. So in this case, our tau equals RC. It's called, in fact, the RC time constant. So we can express this, therefore, as Q equals, either CE or Q max will work for that. Q max times 1 minus e to the negative t over tau, where tau equals RC. So this is it right there. That is our time dependence of the charge on the capacitor. Let's make sure that works. At time equals infinity, this becomes 0, and then we just have the Q equaling Q max, which works perfectly. Now, the next fun part is discharging. So what are we going to do for discharging?